This is the Forces and Motion lesson number 15 to 17 for forces, friction, and the net force. Many years ago, in fact it was 1666, Sir Isaac Newton was sitting beneath an apple tree.
Finally, a little downtime. Now let's find out who exactly this Harry Potter chap is that everyone seems to go on about.
When suddenly an apple fell out of the tree and hit poor Sir Isaac Newton on the noggin.
Well, I sure am most certainly relieved that this is an apple tree and not of the coconut variety.
The trauma from the entire event led to Newton's 3 laws of motion. The first law of motion: an object in motion will remain in motion, and an object at rest will remain at rest unless acted upon by a force. So let's consider the following scenario. It's a nice, sunshiny day, no traffic. Before you know it, there's going to be some kid probably on the sidewalk saying, "Hey, push me!" But he's not going to go anywhere because there's no one to push him. Because an object at rest will remain at rest unless acted upon by some force. Now, don't get me wrong, there are some forces that are being applied at this moment because we know gravity is pushing us down and the ground is pushing us back up, but those two cancel each other out. So there is no what we call net force to get this kid moving. So he can sit there all day. He is going to remain at rest unless he gets a shove. Now let's suppose there's some big pinball type machine that all of a sudden shoots out and gives the kid a shot from behind. Well, that would create an unbalanced force that then starts him moving, and he will remain moving forever. You see, the force of gravity is pushing down and the ground is pushing back up. But we had an unbalanced force when the kid experienced a shove from behind, and that got him moving. And he'll keep moving and moving and moving and moving and moving and moving. As long as there's no unbalanced force to slow him, he'll keep moving forever. And of course, we know that's not true unless this kid was pushed and suddenly found himself in
space.
And of course, this kid is going to keep moving forever because an object in motion will remain in motion unless acted upon by some unbalanced force, causing it to come to a stop. And of course, with our worldly experience, we know that when we give someone a shove on a cart, eventually they will come to a stop because of something called friction. The force of gravity is pushing down, the ground's pushing back up, they cancel each other out. As long as we're moving though, there's something always trying to slow us down, and that is a force called friction. If we stop, friction then disappears. So that unbalanced force of friction brings the kid to a stop, and he will remain at rest until some new unbalanced force causes him to move again. The second law of motion: net force is equal to mass times acceleration. So the second law of motion brings about the equation Fnet equals mass times acceleration, where Fnet is the net force measured in newtons or kilogram meters per second squared. You should make a note on your sheet that capital N is a newton. M is the mass measured in kilograms, and A is acceleration measured in meters per second squared. Hey, you guys got time for a story? Well, let me tell you about this one time. that I saw my kids in the backyard and Porter's sitting in his red wagon and Paisley's trying to pull him around the yard. And it was a terribly boring ride because, well, Paisley was pretty small at that time and they were barely moving. Acceleration was terrible because she couldn't really apply that much force to the wagon. So they asked if I would pull Porter in the wagon, and that was a much better ride because, well, I could apply a larger force. And as you can guess, the acceleration was much better. Hey, I knew there was a point to this story. Remember when I said force equals mass times acceleration? Well, we got that equal sign in there, which means the left side always has to equal the right side. And when I started pulling the cart, the force increased. And if the left side of the equation gets bigger, that means the right side of the equation also has to get bigger. And since the mass didn't change because it's still Porter in the wagon, that means the acceleration had to increase so that the left side would still equal the right side. So acceleration increases when the force is increased. Hey, do you got time for another story? Well, just thinking back to that day I was pulling Porter around the yard in the wagon. And everybody thought that sounded like a good, fun time. So before you know it, it's not just Porter, it's Porter and Paisley and Bruno and Fuzzy Cat in the wagon. And now, well, my acceleration isn't quite as good because it's tougher to pull all these things around than it was just pulling Porter in the wagon around. Hey, I guess this ties into what we're talking about again, because force equals mass times acceleration, and we said we got that equal sign there. And since the force did not change because it's me pulling the wagon, the left side did not change, that means the right side can't change. So mass times acceleration has to stay the same. And we know the mass increased because, well, there's more things inside the wagon. And when the mass increased, the only way for this to remain equal is for acceleration to decrease. So, acceleration decreases when the mass is increased. The third law of motion. For every action, there is an equal and opposite reaction. When I was a kid, I remember stepping off the boat onto the dock, and I thought to myself, I can make that gap. So when I stepped, I fell in the water. Because when I stepped forward, the boat moved the opposite direction. And this brings about Newton's third law of motion. For every action, there is an equal and opposite reaction. So what is a force? Well, a force is any push or pull on an object. This includes things like wind pushing you off your bike, slingshot pulling a rock forward, getting pushed out of bounds by a defensive back in football, pushing a puck with your hockey stick, or getting pulled to the ground when you fell out of that tree. Now on to friction. I want you to pause the video and look up Bill Nye Friction on YouTube and watch that 20-minute video. When completed, come back and finish this lesson. So in the video, we saw that the harder things are rubbing together, the more friction there is, and that friction converts energy into heat. There were also several examples of why friction is important. So we will try to identify 10 things friction allows for in class. Here are some examples, though, if we are not in class. Braking. It's pretty tough to brake if your tires can't grip the road. Gripping. Well, that allows for things like dancing. Otherwise, every time we tried to turn, we'd fall down. Or for holding things, like if I want to have a glass of water, my hand has to be able to grip the glass. If it can't grip the glass is just going to slide through onto the floor, and then I will have spilt my drink, probably milk, and there'd be no use crying over that. Turning. Well, when I'm going down the highway, I know we don't have to do this often in Saskatchewan, but occasionally you do have to turn. And if your tires can't grip the road, when the turn comes, you'll keep going straight. And that would probably lead to a lot of cars in the ditch. Accelerating for trains and cars and combines. Because if you couldn't grip the road, as soon as you started to get your tires moving, they would just spin and spin and spin because they have nothing to grab onto and you would never go anywhere. They also allow for things to slow down, like skiing, because if you went to the mountains and there was no friction, before you know it, you'd be going extremely fast and you would probably only go down the hill one time because you wouldn't survive the trip the first time. As well as the first example in the video was going down poles, because the firefighters, as they go down the poles, are able to grab onto the pole and the friction slows them down. Example 1. A 1,342 kilogram Jetta is pushed by a 650 Newton force. What is the acceleration of the Jetta? So we will start by making a variable list. A 1,342 kilogram, well, kilograms, that's mass, so mass equals 1,342 kilograms. It is being pushed by a 650 Newton force. Well, it says it's the force, so force is 650 newtons. We also see that the unit is newtons, and newton is the unit for force. What is the acceleration? So I am looking for A. Our formula is Fnet equals mass times acceleration. Before I substitute numbers in, I need to isolate acceleration. So to get A all by itself, I'm going to have to move m. Since the two are multiplying, I will divide both sides by m. That way, on the right-hand side, the m's will factor out and A will be all by itself. And A is equal to Fnet divided by mass. So I will sub my numbers in, run it through my calculator, and I get 0.48435. If I look at what I've been given, I have two significant figures in 650 newtons and four significant figures in 1,342 kilograms. So when I'm dividing two sig figs by four sig figs, I should keep two significant figures. So my answer is then 0.48 meters per second squared in the positive direction. I solved for acceleration. I know acceleration is measured in meters per second squared, and I know acceleration should have a direction with it, so I wrote it's going in the positive direction, because that's all the information I have. Example 2, given a force of 27 newtons and an acceleration of 3.2 meters per second squared, what is the mass? Well, we're told the force is 27 newtons, so we put that in our variable list along with an acceleration of 3.2 meters per second squared, and we are looking for the mass. Again, Fnet equals mass times acceleration. If I'm solving for m, I need to get m by itself, and right now A is hanging out around m, so I will move A. To get A away from m, I will divide both sides by acceleration. That way, on the right-hand side, acceleration will factor out. I then have m by itself, and that is equal to Fnet over acceleration. So 27 newtons divided by 3.2 meters per second squared. Punch it into my calculator, I get 8.4375. Now, being that in my given list I have two sig figs and two sig figs, I'm again going to keep just two significant figures, and my answer is then 8.4 kilograms. And that's the end of the lesson. You're good to move on to the assignment.